So far in chapter 12, what we have done is we have been comparing two population means. So in 12.1, we were comparing two means and seeing whether the difference between the population means was zero, or whether it was greater than zero, less than zero, or just not equal to zero. But in 12.2, we were doing the same thing again by looking at the differences, but we were looking at the mean difference between two samples and seeing what that would tell us about the mean difference between two populations of data. Okay. The thing was, in 12.2, these things weren't independent. Okay, they were two things that were very much related to one another. So let's say you had a sample of test scores before someone took a prep course, and then you had the sample of test scores after these people had taken the prep course, and you could see, of course, that the test scores went up. Okay, so these were not independent samples, they were related in some way, whereas in 12.1 you were dealing with two independent samples and comparing them. In 12.2 they were not independent, and then we compared the mean difference. In 12.3, we're doing the same thing we did in 12.1 with the means, but this time we're dealing with population proportions. So we are looking at two independent populations, and we are comparing the proportions of people or things in these populations that have a certain characteristic, given that we know the sample proportions, where we take a sample out of each one of the populations. We're going to compare the sample proportions and therefore see what that tells us about the difference between the population proportions. So the way that we always draw this, we're going to take population 1 and we're going to take population 2. Okay, and population 1 we're going to say has proportion, we'll call it P1, and population 2 we're going to say has proportion P2. Then out of each one of these populations we're going to take just a sample. Okay, so this is going to be sample 1. And out of population 2, we're going to get sample 2. And then in sample 1, we're going to say that the proportion of people in that sample that have this characteristic that we're looking at is going to be P1 hat. And the proportion in sample 2 that have this particular characteristic is going to be P2 hat. So we want to look at the difference between P1 hat and P2 hat in this hypothesis test and see how that is going to affect the difference between those population proportions P1 and P2. Couple of ways that you can do this. Okay, again, this is going to be a hypothesis test, and it's going to be very much the same as last time and what we've done before on a calculator. It's very much the same as 12.1. You're just dealing with proportions now. So whenever you conduct a hypothesis test to look at the difference between the population proportions, your null hypothesis always states that there is absolutely no difference between P1 and P2. So P1 is going to equal P2. Your alternative hypothesis, again, could be one of three things. Okay, they're either not equal to one another, which would make P1 minus P2 not equal to 0. You could have that it's greater than 0, or you could have that it's less than 0. So the second one tells us that P1 would be greater than P2, so there's a higher proportion of people in the first population that have this characteristic than in the second. Or in that third example, we've got P1 minus P2 is less than 0. That would mean P1 is less than P2, so we have a lower proportion in that first population that have this characteristic than in the second population. Okay, so we're going to conduct a hypothesis test for a particular scenario to see whether we want to reject our null hypothesis in favour of the alternative, or whether we're going to fail to reject that null hypothesis. The way that you do this on a calculator is by using a two proportion z-test. Okay. We're going to use a two proportion z-test here, and it works very much in the same way that we did the two sample z-test. You just have proportions and sample proportions this time instead of sample means. Your test statistic for this, if you were to go the long way around, you could do a test statistic and then use the significance level to find the critical value and do all that stuff. The test statistic in this case, it is not a very nice formula. I have written it all down. I will write it all down, and we can talk about it very quickly, but it's not the nicest formula. And by the way, you do not have to remember this because you will not be calculating this thing by hand. Okay. This is the formula, and it looks horrible, and all it is it's the z transformation of the difference in the sample proportions. So it's a z transformation of the difference in the sample proportions. Think about it in the same way that we did when we did the z transformation for the difference of sample means, okay? We have our difference in our sample proportions here, in the same way we had our difference in our sample means, minus the difference in the population proportions. Now this thing is going to equal 0 because that is always the value that comes from here. Okay, P1 minus P2 is going to be 0. So that actually cancels out. This thing on the bottom is just the standard deviation of the difference in the sample proportions. It's horrible. You don't need to know where it comes from, and you are not going to be calculating this thing by hand. Just as a heads up, they have simplified this slightly and used this P bar. All P bar is saying it's x1 plus x2. That's the number of people in each of the samples that have this characteristic. So x1 is the number of people in sample 1 that have the characteristic. x2 is the number of people in sample 2 that have the characteristic. M1 and N2 are just the size of the sample, so sample 1 and sample 2. As I said, it's not a very nice formula. You don't need to know it. All of this can be done in a calculator, and it will figure out that test statistic for you. Okay. Now, if you did use this test statistic and compared it to a critical value, if you did go that route, the critical value is calculated exactly the same way as we've always done. Okay, you're going to be given a significance level alpha, and then depending on what your alternative hypothesis was, you can go ahead, draw in your normal curve, and you can look at whether you've got a two-sided alternative hypothesis, split that alpha between the two areas here and here, and therefore figure out your critical values. Or if it's a one-tailed alternative, let's say it's a right-tailed alternative hypothesis, so it's up here, you can figure out your critical value where the area under the curve here is alpha, and then you can go ahead and figure it out with inverse norm, okay? So it's exactly the same as what we've done before, but you are not going to have to go through all of that because there is a method on the calculator, as always. If you go ahead and figure out, oh, I shouldn't have erased that. If you go ahead and figure out on the calculator, there should be something called a two proportion z-test. It's exactly the same places where we found everything else. On my calculator, it is option 6 on that menu, where you go to stat and tests, and you should find a two proportion z-test. It will ask you for x1, n1, x2, n2. x1 is the number of things in the sample from sample 1 that have that particular characteristic. So x1 is the number of things in sample 1 that have the characteristic. n1 is the size of the sample. So if you do x1 divided by n1, it should be the first sample proportion. Okay, so if x1, we'll actually write it like this, p1 hat should be the number of things in sample 1 that have the characteristic, whatever that characteristic may be that they're looking at, divided by the number of things in the sample. Okay, so all that is just x1 over n1. Okay, so same thing with x2. You are looking at the number of things in sample 2 that have that certain characteristic. n2 is the size of that sample. Then you can pick whether you've got a two-sided or a left or a right-tailed alternative hypothesis, and you can then go ahead and calculate, okay? And that will give you, as always, your test statistic. It will give you a p-value that you can compare to alpha, the significance level that they give you, and you can determine what to do with this hypothesis and whether you're going to reject the null hypothesis or fail to reject it. In my notes, I have given you a particular example, and it says, this is at the bottom of page 2 on my notes, and it says the US Census Bureau conducts annual surveys to obtain information on the percentage of the voting age population that is registered to vote. Suppose that 410 employed people and 487 unemployed people are independently and randomly selected, and that 221 of the employed people and 211 of the unemployed people have registered to vote. Can we conclude that the percentage of employed workers, P1, who have registered to vote exceeds the percentage of unemployed workers, P2, who have registered to vote? So in this case, as always, your null hypothesis, you're always assuming that the difference between the two is 0. Then your alternative hypothesis, you are looking at the difference between P1 and P2 again. And they have said that they want to conclude whether the percentage of employed workers, P1, who have registered to vote, exceeds the percentage of unemployed workers, P2, who have registered to vote. So they want to know, is P1 greater than P2? That would mean P1 minus P2 is greater than 0. So you have your null and alternative hypotheses. Okay. Now, when you run a 2 proportion z-test on this, okay, x1 in this case is going to be the number of employed people in that sample that have that particular characteristic, so it's going to be 221. And then the number of people in that sample was 410. Then x2 was the number of unemployed people that are registered to vote in that sample, which was 211. And then the number of unemployed people in that whole sample was 487. Okay. We have a greater than alternative hypothesis, and then we can calculate. So in my calculator, I get a test statistic that is 3.1579 roughly. Okay. My p-value is really, really small. So I've got 7.945 by 10 to the negative 4. So that's going to give me 0.000795. Okay. Now, in this, they said, in this example, that alpha, they wanted it done at a 0.05 significance level. So 5% of the time, they want to reject their null hypothesis. We can already see here, P is less than alpha. So we know that we're going to reject our null hypothesis. So that means for this particular test, take it back to what this means in terms of the problem. We are rejecting our null hypothesis in favour of the alternative. That tells me that in voting age people, there are a higher proportion of employed people that are registered to vote than unemployed people. Okay, so always bring it back to the problem. Now, in this case, we had a one-sided alternative hypothesis, but as always, if you have a two-sided alternative hypothesis, what is the other way that you can conduct one of these tests? And that is by using confidence intervals. So if you have a two-sided alternative hypothesis, okay, you can use confidence intervals to conduct a hypothesis test. Okay, so in this case you need a confidence interval, and it's always a confidence interval surrounding the difference in the sample proportion. So in exactly the same way that we had a confidence interval that surrounded those sample means, it's the exact same thing here. Again, it is not a very nice formula. Okay, I will write down what it is. Again, you do not have to remember it. The calculator will do it for you, but I just want you to see what you are actually doing here. And I'm hoping that I'll actually write this here. So the thing that goes under the square root is this formula. So that's what's under that square root. What we are looking at here is you would have P1 hat minus P2 hat minus that particular term would be your lower bound, and then your upper bound would be P1 hat minus P2 hat plus that term. Okay, so that would be your upper bound of the interval. You can go ahead and run a 2 proportion Z interval on the data that is given, and it will give you this particular interval. Okay, so it's exactly the same as before, but now you are running a 2 proportion Z interval. Okay. Now, when do we reject a null hypothesis? When do we fail to reject the null hypothesis? Well, as always, we always look at whether the population mean or proportion lies within this particular interval. Now, the population mean, or the difference in the population proportions or the population means, the same as we've done before, we look at whether 0 lies in there. Okay, so exactly the same thing that we did with the difference in the population means. We looked at whether mu1 minus mu2 lied within that interval. Okay, if P1 minus P2 lied within this interval, we are looking at whether 0 lies within this interval. What does that tell us? If 0 is in this interval, it must mean that this particular term here is close to 0, because the rest of this term, the thing that you plus or minus from this term, is very small. So if 0 lies in this interval, it must mean that these two things are close enough together. Okay, if 0 is in there, it must mean that P1 hat is roughly equal to P2 hat with some error. Okay, if that is the case, it means your sample proportions are close enough together. In that case, we can consider our population proportions to be close enough together. Okay, if your sample proportions are close enough together, it's probably a good approximation that you could say that your population proportions were close enough together. So if 0 is in here, we are going to take our population proportions to be equal to one another, and we will fail to reject that null hypothesis. So if 0 is in the confidence interval, okay, that must mean that our sample proportions are roughly equal, which means that we can take we can say that our population proportions must therefore be roughly equal, so we fail to reject our null hypothesis. Okay. There is an example of this on page 3 of my notes for today, and it's another homework problem. And it says a telephone service representative believes that the proportion of customers completely satisfied with their local telephone service is different between the South and the Midwest. Wherever you see that word different, you know that you're dealing with a two-sided alternative hypothesis. Okay, whenever that word different is used. So that means that we're dealing with an alternative where we have a does not equal 0. The representative's belief is based on the results of a survey. The survey included a random sample of 840 southern residents and 940 Midwest residents. So we've got N1 is going to be 840 and N2 is 940. 386 of the southern residents and 555 of the Midwestern residents reported that they were completely satisfied with their local telephone service. Find the 80% confidence interval. So your confidence level in your calculator would be 0.8 for the difference in the two proportions. So we're going to find that confidence interval, okay? But in this case, I've also written down this null and alternative hypothesis to see whether we would want to reject or fail to reject the null hypothesis. Can we say that there is a difference between the proportion of people in the South and the proportion of people in the Midwest that are satisfied with their telephone service? Well, when you conduct this on a calculator, you're going to use a 2 proportion Z interval. Okay, so not a test, this time we're going to do an interval. Because we've got a two-sided alternative hypothesis, you can either go ahead and do the 2 proportion Z test and go that way about it, or you can do the 2 proportion Z interval and see if 0 lies in the interval. So in this case, when you run that, the 2 proportion Z interval ends up being negative 0.161, to negative 0.1008. Okay. 0 does not lie in that interval. Okay. That means that our sample proportions are far enough apart that we can therefore not say that our population proportions can be equal. So because 0 is not in this interval, we're going to reject our null hypothesis. Okay. So this is exactly the same as what we did in 12.1. But in 12.1, it was split into two parts, whether we used a 2-sample z-test or a 2-sample t-test, depending on whether that population standard deviation was given or just a sample standard deviation. In this case, we are dealing with proportions, but it's the exact same theory behind it, okay? You can either go ahead and do a 2-proportion z-test, okay? Go ahead and do the 2-proportion z-test and you can compare the p and the alpha value as always, or you could go the long way and compare the test statistic to a critical value. Or if you have a 2-sided alternative hypothesis, you could go ahead and do it this way, where you find that confidence interval and then look at whether 0 lies in that confidence interval or not. Okay, so it's exactly the same as what we have done before. Go ahead and try some of the practice problems. They are very similar to this, and go ahead and look back through my notes where I've got a couple of these examples again so that you can see where this has come from. If you have any questions, please let me know, and I will see you in the next video.